Today we are going to talk about compression and retention policies and not only the policies, but how they work internally and why they are good and what are the architectural aspects that makes it a great decision to adopt these technologies and these techniques, right? So as you know, we are on Timescale/templates. That's our GitHub for everything that we are doing here. And we have a pull request open for the sensors data. Yesterday, I added more and more things to this pull request, and we are building a template for sensors data. And the good part is that we are trying to keep it a very flexible and extensible template. So we have variables for everything. So we can define the name of our business, the type of the data that we are going to store, and all details. And then we can reuse it along of our template to be binding the values. Like in this case, we refer to the previous variables with column hypertable. It will bind the name, and then we can keep adding more and more features to our initial SQL system. So this is how it looks when we bind. In this case, the table we are talking in this example is a sample, and this is like collecting sample from different devices into a specific time, and every value is a new row on this. And this is also a hypertable that is automatically partitioning it in 7 days. So every 7 days you have a new partition, and then Timescale takes the responsibility of like splitting the data and collecting data from different sources depending on what you are doing. For the continuous aggregates, we build a more dynamic SQL schema that we can allow, we can build multiple hierarchical continuous aggregates, one in the top of the other. So we agree on having like 1 minute, 1 hour, 1 day, and 1 month periods. And you can see that the first the minimal time frame, the first continuous aggregates is the only one that is not hierarchical. It goes to the raw data in the hypertable, and the rest of the continuous aggregates are hierarchical, and they are inheriting and rolling up data that's already pre-processed in the previous time frame. So we analyzed it in the past. We saw how fast it is and how good is this type of things, and now we are moving into this session that is all about, let's say, background jobs. So most of the things like they can run upfront, but they run in background jobs. And they run in background jobs because they are policies. So policies are basically metadata about things and things you want to keep and how you want to keep your data life cycle, and details are spread in this jobs metadata. And then we have like background jobs that are a runner that can get this metadata and apply a specific function and make it work. So we are going to cover both compression and retention. So let's start with compression. Compression and retention, I forgot to mention this. They are very simple, just like these 2 lines of code that you just say, hey, here is my policy. Just like after 1 week, compress my data. After 6 months, just like drop it, and that's it. So for compression, I love this reference. This is a community reference, someone that just installed Timescale, enabled compression, and got 34 terabytes into 2 terabytes. So if you think about like how crazy is reducing the data in this way, like it's really where Timescale operates in your savings and make you save money, right? And this is the average of what people report for us. They report in average 95% compression ratio. So this looks really good compression ratio. And this means that you are just using 5% of the storage that you are supposed to use, right? So what means that you can store 20 times more data than what you would originally have in the same database, right? So here is the template setup. You just need to enable compression and just say your hyper table, a few configurations. So the first configuration we have there that's very important is segment by. So segment by generally comes from your business, and this is where the compression really shines, because when we segment by some specific business data, so in our case, we are segmenting by device ID. So it means that we will have like a compression over all the columns by this segment. So let's say the columnar compression will get the values, and we'll build a compression algorithm for the sequence of values available. We are going to go deep into the algorithm soon. The second option is the order by. That is also very important, and the order by will also make really fast query scanning when you know, for example, oh, I would like to have the last line or the first line, and then you can get this working. We also have a few extra arguments, and I would love to also call your attention, because this is like sorry, not new. The new is only the last one. The other two are old, and they are very important. They are optional, but for performance, they are really required. So really go and tune your params for this. So segment by is this one that will make your columnar storage much more easy to create, like let's say a reasonable series. So imagine, for example, if you are storing data from multiple sensors in the same table, right? So you have a temperature and humidity. So you are receiving 10 for temperature and 75 for humidity. And then like you have 10, 75, 10, 76. And so this is the type of sequence that will keep jumping and will not build a consistent series, right? So you need to also think about these small details. And for compressed chunk time interval, it's very interesting that you can get multiple chunks and end up compressing them into one. And then when you uncompress them, they will come back to the previous state and decompress into multiple chunks as it was before. So this is a new option. It's good because sometimes you compress and then you have, oh, this chunk is so small, I could compress multiple. So now you can pack them together using these options. And it can also be very useful for keep enhancing and let's say molding the size and of your chunks. So let's talk about a few of the compression advantages. And the first thing is that it compresses, it's all or nothing. So you have the entire chunk being compressed. So the only locking moment that you have is when you are swapping the data. So you generally do it with, let's say, very old chunks that are let's say not being touched. So you already know your data is let's say freeze. So and when you have like the new compressed chunk, it just swaps the reference. So it's just a single moment. And you also have less indices and more segments. So instead of creating more indices to find where your data is, you segment your data, and with these segmentations, you kind of have a map of where your data is, and then you can just get the right compressed packages that belongs for the data that you are querying. And in the end, you have a lot of storage savings, right? So let's talk about how it works behind the scenes. So behind the scenes, compression is a kind of a mathematical simplification or maps of things that can be, let's say, smartly replacing parts and fragments that are repeated. And there are several different approaches. Some of them are for math and some of them are for text. So let's go one by one now, and let's take a look in this example. So let's say we have this temperature. This temperature is storing CPU, memory, temperature, and humidity, right? So this is our table of example, and we are collecting this data. And then if we apply a delta encoding, so we would just be getting the deltas of the next line. So if the temperature was 8 and jumped to 81, I would just have a 1 in the next temperature. So it knows that it's the first value plus 1. And then if the next value is the same, I will just have 0 because I will not changing the value. So and the humidity is the same. So as you can see, from bigger numbers, we get into smaller numbers, and you can see the same on memory, 3 bytes, for example, you get the ups and downs of memory, and then that's how delta encoding works. And then you can think about, wow, but we can go one level late, one level more deep, and just get like the deltas of the deltas and make it even smaller. So that is like, for example, here you see the time. So time here is coming with a 5 seconds delta from the first one, but the delta of the delta will just make it 0, right? So, and you keep getting things shorted and shorted, and in the end, for unfolding such expressions is quite easy, and it's not that expensive. So this is one type of algorithm. And then let's think about repeated values. So let's say you are like getting temperatures. So temperatures are just like same temperature for hours or just slightly changing. But if you have, let's say, high resolution of your data, let's say, for example, you are storing your data into 1 minute, and then you go to 10 seconds. So maybe, oh, this 10 seconds value will be very, very similar. And then in the end, you can say, well, you have 111 and then you have 612. So it will just change from 6 to 12 or to 20 and make the series larger. So this is very, very useful, and also used for very, very large amount of algorithms, right? Dictionaries are everything that is a text. So if you are using text anywhere, it will try to get your text and build a dictionary. Any word that's repeated inside the text will belong to the dictionary, and then it will just say like, well, put this New York and this space. So probably it will say like, oh, this is \0, \1, \2, and then it will just switch the reference in the main text using this reference of the dictionary. And we have also other types. So we use gorilla compression for floating points. It's a very interesting algorithm, and also delta encoding for integers, the delta of delta for timestamps, and dictionary in general for text or category data. So, for example, if you are storing like a device ID that's like a UID or a text, it will also be trying to be encoding it into this type of dictionary. And now let's talk about a new feature that is not that new because it's already like 1 year, a bit more around, but this is very interesting. That's how we make our compression flexible. So in the past, compression was like, hey, you compress something, you cannot insert data there anymore, you cannot update data there anymore, and people need to backfill data. They need to consume all their old data, it needs to be recompressing. So let's talk about it and how it works. So let's imagine this scenario where we have a compressed chunk, and then we have this uncompressed chunk coming to become a compressed chunk. So let's take a look and take a moment to analyze what we have here. So we have basically a large list of rows that we are packing into a columnar storage. So if you check the temperature is just aggregating all the values, as the same is happening with device and status code. So you just transform your columns into, let's say, your rows into columns that has arrays of values, right? So you are packing 7 rows in one single row. In the compression system in general, the batch size can be up to 1,000 values. So if you are compressing and you don't reach 1,000 values by your segment, so for example, let's say you have a device ID that is not emitting like 1,000 values per segment, maybe it will have a slightly slow compression ratio, right? So that's the type of thing that you can expect. But the point here is not about what happens now, but how it deals with data change. So let's say we are going to add some data here. So a new tuple arrives. We have a new data that should be compressed, but this data belongs to the first compressed chunk. So how are we going to do? So if we put it there, we will have a very poor compression rate, and then we will have just a single line being compressed alone. So this is really a nonsense thing. But here is how we are dealing with the problem. So we have this moment that we have this that we call it, let's say, staging area. So this staging area is where we keep the data that is still, let's say, fresh and new data. So if you are querying something for this compressed chunk, it will go to all compressed data plus the data in the staging area. And then it will just say, well, let's mark it to recompress. And then let's imagine that we have more of this. So we will, let's say we come from this tuple that is in the staging area, and then we go to recompress the chunk. So recompress means that we are going to decompress, merge that staging area, and compress again. So the uncompressed chunk will just put that line in the right position, and then the new compressed chunk will just have the line back. So that's how it works. And in the end, the staging area will be empty again, right? So if you are doing a lot of changes in your data, it will not be, let's say, recompressing immediately. So you can do a lot of changes. They will be all in this staging area, and then you can recompress them once at a time later, and let's say perform this task only once. So if we have like a reactive process where you change data, you try to recompress, that would mess. But in this way, we just say, well, this is dirty, we need to recompress, and that's a way that it makes it really, really fast. And what if the compression ratio is too low? So this is a very common question. I have a lot of office hours with the folks, and this is a thing like people, hey, I saw and everybody has a very nice compression ratio, and then I'm trying to compress and my compression is not working to do. So a few things that you should be thinking about compression is if you have too many columns. So let's say you are trying to compress 50 columns, maybe one of your columns or another column will not compress well, or 10 of them. So one idea I always suggest is try to go and split your data into several hypertables and compress them independently. Then you find what are the offenders and what data is not compressing well. And also be careful with the toasting system, because we also have this way that you can store large objects in the database. So if your data doesn't fit in a row, in a column, it will just use this extra table from the toast system to store your data there. So it will not compress well as well. So you need to be careful with this. And yeah, so these are small things to keep in mind. Moving on, we talked about having 20 times more data because we can build great compression system. Now let's talk about having 20 times less data with our data retention. So that's the idea. And the first thing that we should think when we think about compression is that we are building a control for our data size and our data growth. So if we stable something, we can just say, well, we go until this moment, and that's the limit. So for example, if you have like a retention policy of 6 months, so when your chunk completes 6 months old, when the last data of your chunk completes 6 months, it will be dropped from the database. It will be completely dropped. So let's think about how the data grow works and what we can do for that. So let's imagine that we have 1 billion rows per day in an average of like 100K devices. So 100,000 devices are emitting average 1 billion rows per day. So it means that if we have a retention policy of 6 months, we will have almost 200 billion rows, but that's all. That's all the rows of my, let's say, fresh data, and this is the full size of my data. So it will never be more than that, because when things gets older, it will be doing it. If we have one day, we will just have 1 billion rows. So and then for example, let's say if we have one day 1 billion rows plus aggregating 100,000 devices, let's say we are building some candlestick or some average or some status of our data in the minute level. So if we have 100,000 devices, we will have 360 million rows per day from this data. That's aggregated data. So we have almost this, let's say, extra 2.4 million for 1 hour plus 100K for 1 day. So if we are just doing hierarchical, so in average, we have 1.4 billion rows per day, right? And knowing this number, we can just try to stretch and make it scale and see like, hey, for 1.4 billion rows, I need the X gigabytes or terabytes, and then you can allocate it, and then you know that your cost will be limited to this time, right? How it works and why it works, it's so cool. And it's so fast that you can't believe how fast is this system. So the key thing of this is truncate. So if you're not familiar with truncate, truncating is the most fast method ever. So it means like when you are going to say delete from table and with no where clause, it means that you want to like drop the table. If you do delete from without the where clause, it will go row by row and just say, well, go and delete this data. If you do, for example, delete with a where clause, which you say from time range A to B, destroy this data, it will also be going row by row. So imagine if you are storing 1 billion rows per day and just try to scan a few 100 billion rows to try to delete them. So it's very, very expensive. So if we have a chunk per day and we use a truncate, the thing is that we remove the whole chunk. And saying remove the whole chunk, the chunk is the table, is the table that contains the data about a specific partition, for example, first month or second month. When you destroy the table, you also destroy the statistics, because the statistics are in the header of the table, so you don't need to do any vacuum work. So the most expensive thing on delete is that when you are deleting, you are not actually deleting, you are marking something as invisible and deleted at, and then when the system is running, it's just skipping this line and going to the next line, but it's really there. And when you truncate, you just do like echo/dev/new now to the file name. So you destroy the file. You just like swap the file. And that's why it's so fast. And all the indices are truncated together. So you don't need to do any extra updates. everything is very well segmented as necessary. I just want to invite everybody to join our discussion sensors. That's where we are continuing these discussions and conversations. And if you are not on our TimescaleDB Slack, join us. We have a community that is always sharing cool stuff. And we have several discussions going on. So we have discussions around finance, around sensors. Soon we will start discussions on the metrics ecosystem and how to build a small metric system using Timescale. And I also offer office hours with the folks that are eager to learn or have any questions. So office hours is the perfect program to have a one-on-one with me and talk about your Timescale project, and I can help you as I can. So thank you very much. And that's all we have for today. Thanks for joining. See you next time.